Have you ever wondered what's really going on inside your smartwatch or your coffee maker? Well, there's a tiny, super powerful brain in there, making billions of decisions every single second. Today, we're going to peek inside one of these brains and see how it really works. And when I say it's everywhere, I mean it's everywhere. The hero of our story today, the Stm32 Cortex-M4, is this incredible high-performance processor, and it's the silent workhorse behind countless devices you use every single day. It's the reason our gadgets are so smart and so efficient. All right, so here's how we're going to break it down. First, we'll get to know our microscopic hero. Then, we'll see how it juggles dozens of tasks at once, what it does when things go completely wrong, how it keeps its memory safe and sound, and finally, why all this makes it such a tiny titan of efficiency. Okay, let's start at the beginning. Our protagonist, the Cortex-M4, is a high-performance 32-bit processor. Now, it's specifically designed for the world of microcontrollers, which means it's built to be really powerful when it needs to be, but incredibly power-efficient the rest of the time. Now, you gotta understand, a microcontroller isn't like the big CPU in your laptop that's running a whole operating system and a dozen different apps. Think of it more like a specialist. It's a whole computer on a single chip, totally dedicated to doing one main job, like managing your car's engine or tracking your heart rate and doing that one job absolutely perfectly. So, the first big challenge in our microcontroller's day is multitasking. I mean, think about your fitness tracker. It has to monitor your pulse, count your steps, and update the time on the screen, all at the same time. But here's the catch. It only has one core, one single brain. And that's the million-dollar question, isn't it? How does it do it? Well, the answer is a really clever and incredibly fast system for managing priorities. A system that revolves around something called an interrupt. An interrupt is exactly what it sounds like. Let's say your tracker gets a new heartbeat reading. A signal literally interrupts whatever the processor is doing. It's like getting a VIP phone call you just can't ignore. The processor pauses what it's doing, saves its place, and immediately handles that urgent new info. This is the secret to making a device feel snappy and responsive. But here's the thing. Not all VIP calls are created equal. As you can see here, the processor has a super strict priority list to manage all the chaos. Right at the very top, with the highest priority, is a reset. That's basically the system's fire alarm. Everything stops and you reboot. Right below that, you have the NMI, or non-maskable interrupt. The key word there is non-maskable. It means this is an emergency signal, maybe a critical power failure warning, that the software is absolutely not allowed to ignore. Next up are hard faults, which we'll get to in a sec. And then you have everything else, like the system's little heartbeat timer, which gets a priority that developers can actually configure themselves to fine-tune how their device responds. Okay, so that priority system is amazing for handling events from the outside. But what happens when the VIP call is actually a bad connection? Or when the code itself is the problem? You know, software has bugs. So the next big challenge for our little brain is handling these digital disasters without having a total meltdown. The first line of defense is catching what we call usage faults. These are basically common programming mistakes. The most famous one, of course, is trying to divide by zero, which you just can't do. Instead of crashing, the Cortex-M4 is smart enough to spot this, raise a usage fault, and let a special error handling routine take over. Now, things get a bit more serious with a bus fault. This happens when the processor tries to access a location in memory that either doesn't exist or is invalid. It's like trying to find a house that just isn't on the map. It's a fundamental memory error, and the system needs to know about it right away. So, if a usage fault or a bus fault happens and there isn't a specific piece of code ready to deal with it, the system doesn't just give up. The problem gets escalated. It's sent up the chain of command to the ultimate digital backstop. The hard fault. Yeah, this is the big one. It's the processor's catch-all for critical errors. It has a fixed, super high priority, which means it overrides almost everything else. It's basically the processor's way of screaming, something has gone very, very wrong, and I need to stop before I cause any more damage. It really is the blue screen of death for microcontrollers. Okay, so the processor can catch all these different kinds of errors. But this brings up a huge new question. With so many different tasks running and the potential for faults everywhere, how do you stop one buggy program from scribbling all over the memory of another one and taking down the whole system? Well, the solution is this awesome piece of hardware called the Memory Protection Unit, or MPU. You can think of it as a dedicated security guard, or maybe a bouncer for the processor's memory. Its only job is to enforce access rules, making sure every program stays in its own lane and doesn't mess with anyone else. And here's how it does it. The MPU basically divides the system's entire memory into these distinct regions. It can create up to 8 of them. The best way to think about it is like this. Memory is a big apartment building. The MPU is the building manager, and it gives each program a key that only opens the door to its own specific apartment. You can't get into your neighbor's space, and they can't get into yours. Simple as that. And the rules for these apartments can be incredibly specific. The MPU can mark the area with all the program code as read and execute only, which means a bug can't accidentally overwrite its own instructions. And here's the real so what moment. Think about your car. The code for the radio and the code for the anti-lock brakes are probably running on the same system. The MPU creates a firewall between them. A bug in your music app can't possibly access the memory used by your brakes. That's not just some neat feature. It's a critical safety net that makes these devices trustworthy enough for life or death situations. Okay, so we've seen how our Cortex M4 brain juggles tasks, handles disasters, and protects its own memory. So let's tie it all together. What's the big payoff here? Why does all this elegant engineering matter for the actual devices we use every day? Well, what do you get from all this cleverness? First off, speed. That interrupt system means your device is always responsive, no lag. Second, incredible battery life. These chips have integrated sleep modes that let them just sip power, which is why your fitness tracker can run for weeks. Third, safety. As we just saw, that MPU provides an ironclad safety net for critical systems. And finally, you get pure efficiency. It just gets more done with less code and less energy, which is pretty much the holy grail for any smart portable device. So when you put it all together, what you have is this tiny, tough, and incredibly efficient brain. There are literally billions of these processors quietly working all around us, powering the smart world we live in. And that kind of leaves us with one final thought. What challenges are they going to help us solve next?